mostly here. I want to get 7-8 finished today, so here are a few more type 2s to deal with. Before I do that, I thought I'd maybe try and simplify what we mean when we say an integral converges or an integral diverges. So here is about the simplest way I can describe it. Okay, so when we say that an integral converges to 4 or 44, what we mean is that the area under this curve is 4. So when we say it converges, we mean that the area under the curve is whatever the number that it converges to is. However, when we say that the integral diverges, what we mean is that the area under the curve is either infinitely large, right? Its area is infinite, or it doesn't have any fixed value. In other words, the area under the curve can't be made into a number. It's just any old number. It keeps bouncing up and down and changing values. Sin x would be a good example of that if you were doing a type 1. So what I've done is I've picked a couple of homework questions and one more my own. Kept them all basically at the same place where the vertical asymptote is happening. If you look at question 23, 25 and the one under it, do you notice that it's x equals 1 is the problem? Right, at x equals 1, the denominator is 0. That means there's some kind of weird thing happening there, probably a vertical asymptote mostly. So we'll start with 23. If you want to find the integral from 0 to 1 of 4 over the square root of 1 minus x squared, you've got to realize that 1 is causing the problem. So this is going to be the limit as t tends to 1 of the integral from 0 to t of that guy. So it basically figure out what value of x is causing the vertical asymptote. If it's one of the limits as it is here, do that. And now what we can do, actually we can do it here, is the limit as t tends to 1, and you integrate this guy. Do you recognize the antiderivative of 4 over the square root of 1 minus x squared?
Sine to the -1.
Okay, correct. And that's going to be evaluated at 0 and evaluated at t. So that becomes 4 inverse sine of t's, take away 4 inverse sines of 0, and I almost forgot, it's still the limit as t tends to 1. Now the inverse sine of 0 is what angle has sine of 0, which is 0. So that's 0. And this fella here, when you brute force it, is the inverse sine of 1. What angle has a sine of 1?
Pi halves.
Okay, so it's 4 times pi halves, take away 0, it's 2 pi. So what we've now shown is that this integral converges to 2 pi. So if you took this function and you did a quick sketch of it, and you found out what 4 1 minus x squared looked like, and what would it look like at 0? At 1, it would have a vertical asymptote. At 0, it would be worth 4. So it would probably look something like that. And we're saying that area is 2 pi because it converges. So it actually does have a real area, a physical area of 2 pi. So there's a converger for you. Are you okay with that question? It was pretty straightforward, at least the integration part. Cool. Second one of the set. We're going to look at the integral from 0 to 9 of 4 over the cube root of x minus 1. Now, the problem with this function is at 1, but the limits of integration don't start at 1 or finish at 1, like they did here. 1 is inside this integral, right? It's between 0 and 9. And when that happens, you are going to do the integral from 0 to 1 of 4 over the cube root of x minus 1. And then you're going to do the integral from 1 to 9 of 4 over the cube root of x minus 1. So what you do in any situation where the vertical asymptote happens between the start and the finish, right, between the limits of integration, is that you must split it into 2. And then you find each one, just like we did question 23 or any of the others, right? You find the answer to each of these separately. If this is 4 and that's 22, then the whole thing adds up to 26 and we say it converges to 26. If this is infinite and that's infinite, it diverges, right? So there's our choices. It's going to converge to a number and it's going to diverge. We can save a little bit of time. If we do the first one and the answer's infinity, we don't bother calculating the second one because it's not going to make any difference. If one of these is infinite, we say that the integral diverges, right? It has no fixed value. So I'm now going to separate the question out and do this one. Now, to be able to do this one, we're going to do the limit as t tends to 1 of, are you happy about the negative 1/3 thing? That the cube root in the bottom can be replaced by a negative 1/3 power. Okay, so we're okay with this guy being him. So I can now do, oops. I can now do the limit as t tends to 1 minus this fella. Now you want to integrate him. You add 1 to the power, and then you divide by 2/3, which is the same as multiplying by 3/2. And if you multiply by 3/2, 2, you get 6. And then you evaluate it at 0, and you evaluate it at t. So this now becomes the limit as t tends to 1 minus of 6, t take away 1 to 2/3 minus 6 times negative 1 to 2/3. And I'm going to be essentially doing brute force. So 6 times 1 take away 1 power 2/3. Right, negative 1 to the power of 2/3. What value is negative 1 to the power of 2/3? Well, if you don't know, you could do it in your calculator, can't you? That's why fractional powers with negatives are quite weird things. It might be that the calculator will have a problem with it because its fractional powers are ugly, but not this time. The answer's 1. So negative 6 times 1 gets you negative 6. Which is, well, 1 take away 1 is just 0. Would you agree that 0 to the power of 2/3 is also 0? Would you agree 0 to the power of 2/3 is 0? So what we get here is that the first piece converges to negative 6. Are we go with that? The first piece converges to negative 6. You can then do the integral from 1 to 9 of this fella. And you will get, well, I'll tell you what you'll get. I'll do the whole thing. You're going to get that basically there, but that's not going to be -1 anymore. It's going to be 8. So that's going to be take away 24. So you're going to get 24. And that guy tell us the entire area. That bit's -6, that bit's 24. If I did my calculations correctly, and I did the last one in my head, so it may not be, you get 18. Are we good? And that's how you take care of a type 2, where the vertical asymptote is in the middle of the limits of integration. I'm not going to do this one entirely either, but there's a different reason for that one. So it's going to be from 0 to 1. Call it a negative power. And from 1 to 9, call it a negative power. So 1 is the problem. Convert this to a negative power to make it easier to integrate. And let's just find this fella. Well, he's going to be the limit as t tends to 1, 0 to t, 4 lots of x minus 1 to the power of -3. Okay, if you add 1 to the power, you get -2. You divide by that power, you get that fella, evaluated at 0 and at t. But that's quite difficult to deal with. So I'm going to do some style points on this. I should have probably done some style points in the previous question, but I just didn't. So it's going to be the limit as t tends to 1 of -2 t take away 1 squared minus -2 over -1 squared, which is 1. So we're looking at the limit as t tends to 1 of -2 over t minus 1 squared plus 2. Okay, let's brute force it. -2 over 1 take away 1 squared, add 2. -2 over 0, add 2. Okay, we've seen numbers divided by 0 before. Would you agree that -2 over 0 is infinite? You agree? -2 over 0 is infinitely large. And that means this diverges. If your area is infinite, it diverges. Since this piece diverges, do I really care what the next piece does? No. So won't the entire integral diverges? So when you get a question in the WebAssign and it's the answer is it diverges, all you do is you stick in the box, I think capital letters, diverges. You don't need to go into any specific reason of, write a calculation like that, or in this case, you might do this one and it's plus infinity, and you do this one, it's negative infinity. Don't matter. If one of them is infinite, stop looking. The answer's finished. Okay, that's it. Improper integrals are finished. Any last minute questions on them? Are we good? If we are, I shall move on. Here's our last section for this week, 8.1. We're going to do a thing called arc length. I'll leave this here for a while. You can write them down now or watch the video and write them down there. When you're being asked to find the arc length, what you're being asked to do is, for a function, let's say y equals f of x, starting at x equals a and then finishing at x equals b, the arc length is the distance from here to here. So if you're a little car and you're driving along the road, how far would you travel? Now, would you agree it's not B minus A? B minus A would be on a straight road from A to B. Would you agree in this one? There's a curve, as you'd expect, so won't it be longer than that? And that's the arc length. Now, interestingly enough, you calculate the arc length by using this formula. Yeah. And you notice it's an integral formula, right? It's an integral from A to B. The guy that you integrate is a bit weird. If you want to look at the proof, it comes from Pythagoras, and you can certainly go and look it up. It's the square root of 1 plus the derivative of the function squared dx. So in this one question, aren't you going to differentiate, square things, and integrate things? So you're going to do a lot of different bits and pieces. So just be careful that you've got your differentiation hat on when you need it and your integration hat on when you need it, because you're going to do both. Now, you can also do it if the curve is x equals g of y. So can you imagine the curve was a sideways on one? You still want to know its length, right? But the curve will be x equals y cubed plus y, you know, that kind of look. And you'll start at y equals 10 and you'll finish at y equals 20, right? So you can imagine you could do it that way. The good news is, isn't the formula for all intents and purposes equivalent, right? So if your function is y equals x cubed, you use the top guy. And if your function is x equals y squared plus y, you use the bottom formula. So far, so good? Any questions about that? Okay, let's jump right in and see what they look like. Let's have a function. This is question 2. Should warn you that the algebra is going to be, in some questions at least, quite convoluted. Right, here's a function, x take away 4 log x, and we are being asked to find its arc length from 1 to 4. We use the letter L for arc length, so it's going to be the integral from A to B, the square root of 1 plus the derivative squared dx. So in this case, it's going to be the integral from 1 to 4. 1 plus, if you differentiate this guy, you get 1 minus 4 over x squared dx. Are we okay so far? The derivative is 1 minus 4 over x. And the derivative squared then inside the square root gives us this. Now, you know, I would hope you would know, just looking at that you are not going to get the answer to that handed to you in a plate. Would you agree this is going to be difficult to do? Because aren't square roots horrible things to do integrals with, right? They just aren't pretty. So there's going to be a lot of algebra happening. First thing I'm going to do is FOIL this all out. And 1 times 1 gets me 1. And then I do a little thingy, I get minus 8 over x. And I get plus 16 over x squared. And then I get the integral from 1 to 4 of the square root of 2 take away 8 over x plus 16 over x squared dx. So far, so good. And the good news is that for this question, that's as far as they want you to go. Can you trust me if I had to try and integrate that thing, that it would be another 3 pages of some really messy stuff? So let's just say thank you and move on. So let's do a question that we can actually do all the way through. And here is a straight line. And it's going to be from -1 to 4. So can you imagine what that might look like? There's -1, there's 4. Something like that, right? So would you agree the arc length is just that distance? So it should come out nice. Let's see what we get then. It's going to be the integral from -1 to 4. The square root of 1 plus the derivative of this, which is -4 squared dx. So it's going to be the integral from -1 to 4 square root of 17. Okay, square root of 17. What do you get if you integrate a number, the square root of 17?
Square root of 17x.
Yep. So you're going to get square root of 17 times 4, take away the square root of 17 times -1. So you're going to get 4 square roots of 17 plus 1 square root of 17, and your answer will be 5 square roots of 17. Would you agree that one wasn't too bad? Are we good? Comfortable with that? Right. Let's do one where we're being asked to find the exact value. So this time I'm going to move to 5. And the function is going to be 2/3 x to the 3/2 between 0 and 1. Pictures of you, but smoothies. Come on, go over there. There, that's fair. So what we are looking at is the arc length is the integral from 0 to 1. The square root of 1 plus whatever the derivative of this is squared dx. Okay, differentiation. Multiply by the power, reduce it by 1. If you multiply this by 3/2 and then you reduce it to a half, they cancel out and you end up with x to the half. So we now have the integral from 0 to 1. Well, if you do these, you get 1x. And if I wanted to integrate the square root, I would remember that I can just call it a half power. So the square root of 1 plus x is 1 plus x to the half. That way I can use the power rule, which is add 1 to the power and then divide by the new power. So what do we get? We plug in 1, we get 2/3, 1 plus 1 to the 3/2. Take away 2/3, 1 to the 3/2. I probably should have done this earlier, but I'm going to do it now. That's 2 to the power of 3/2. And that's just 1, so that's 2/3. I'm going to pull out the 2/3, and I'm going to make that guy the square root of 2 cubed, and that guy 1. So what we end up with is 2/3 square root of 8 minus 1. Try to make the answer as nice as possible. I know that looks like 23, but it's actually 2 to the power of 3. Can you do anything to the square root of 8 to make this even prettier? Or what can you do? Because you can do something to that. What can you do to the square root of 8 to make it a little bit prettier?
You can make it into 2 multiplied by the square root of 2.
And we'll call it good. We're finished. So the length of this curve, starting at 1 and finishing, starting at 0 and finishing at 1, is this. You notice you spent half your time just making the answer look pretty. I mean, we'd finished the integral by here, but it took us another 4 lines to get it to look as nice as it could. The style point thing. Not getting a lot of questions today. I guess that's a good sign. Are there any problems with this before I move on? Okay, let's see if we can hurt your brain. Y equals 2/3 1 plus x squared to 3/2. We're going to do it from x equals 0 to 4. Okay, the functions are getting harder and harder. For a question like this, when I look at the function, I say, look, that's going to be quite an ugly derivative. I suggest that what you want to do is just find its derivative. Right, multiply by the power and reduce it by 1, gets you 1 minus x squared to the half. Is there anything else I should be multiplying by? Right,
The chain rule,
Okay, so that means I should finish with times what?
2x.
2x. And then I'm going to do a 1 plus that guy squared. In other words, all the stuff that's going to go in the square root, do it before you do the square roots. Otherwise, won't you be spending lots and lots of lines having to write integral from 0 to 1, integral from 0 to 1, dx. You end up writing a whole load of stuff. So why don't we make it look pretty before we put it in the integral, essentially? Now, this guy, when you square it, becomes, well, let's write it down. 1 plus 2x, 1 plus x squared, that guy there, to the power of a half. If you square it, you get 1, you get 2 squared, you get x squared, and this guy, when you square it, gets you that. Are we cool with 1 plus the derivative squared is this expression? Right. So if you take the 2x, 1 plus x squared, if you take that guy and square it, you square each piece. 2 gets you 4. X, when you square it, gets this. A half power when you square it gives you 1 power. And that 1's on its own at the side. So this is now going to become 1 plus 4x squared plus 4x to the 4. Are we okay? You still with me? Are we okay? Now, you might think, oh God, am I going to stick that inside the square root? Because if you did right now, you'd be in trouble because there's no way you could integrate it. So let me tell you a little trick. The vast majority of the ugly ones, right? To me, anything that's got more than 2 x's in it is ugly. The vast majority of the ugly ones are going to be perfect squares. In other words, this expression is a perfect square, right? It's like x plus 1 squared, right? That kind of thing. Now, this is just me. You don't need to do this line, but I like things to be in order, right? Now we have to figure out essentially factoring this guy, but since I'm telling you it's going to be a square, I have to figure out what guy times itself, if you foiled it out, would give you this guy. This is not the typical.
Is it 1 plus 2x squared?
Yeah, I'm just rewriting it the other order, but what you said is exactly true.
Yeah, the 1 was the easy part.
Right. Well, let's show you how to tackle this general question. I like to put them in order biggest to smallest, but you can do smallest to biggest if you like. But I like it this way. the last term. Now that right now is 1, right? So you were quite right. It's pretty easy to know that's going to be 1. But see if this is 9, will you make that 3? See if this is 25, will you make that 5? Do you see how this is going to work, right? So this term at the end, in this case, the number 1, won't that generate the number that goes here? Now, how do you get from this guy, 4x to the 4, to 2x squared? So going this way, you take the square root of 1 and get 1. What do you do on this side to get 4x4? How do you get 2x squared out of it?
Square root.
Square root. So take the square root of the big term, he goes first. Take the square root of the last term, he goes second. And can you just trust me, but if you don't FOIL it out, this guy, when you FOIL him out, is this guy. So we have now got to the point where we can do the arc length. It's going to be the integral from 0 to 1, the square root of 1 plus the derivative squared dx. It's going to be the integral from 0 to 4 of 2x squared plus 1 squared dx. Do you see why a perfect square works really well now with this formula? Right? Don't perfect squares work really well with these formulas? So what we get is the integral from 0 to 4 of 2x squared plus 1. Won't the square root cancel out the square? Right? They work against each other. And this fella is add 1 to the power, divide by the new power, evaluated at 0 and at 4. So it's at 2/3 times 4 cubed plus 4. Take away a whole load of nothings. 4, 16, 64, 128/3. Add 4. 4 is actually just 12/3. So it's 140/3. And we're finished. The arc length for that particular curve from 0 to 4 is 140/3. Do you like that one?
That was pretty cool in the end.
In the end. Not so nice in the middle, but cool in the end. Here's even worse. I'm going to write them as 1/3 x cubed and 1/4 1 over x. The question actually had them written like that. But I find it helpful, for me anyway, to suck out these numbers as fractional constants. It just makes it easier when I do the chain rule or I do the power rule, because sometimes, especially with guys that look like that, you get a little bit messed up. This fella here is going to be differentiated. Do you notice that he's really 1/4 x to the -1? Now you might say, well, yeah, okay, I trust you. Let's show you what could happen if you didn't write it the way that I did. I'll keep them together. If I had this guy, and I know I have to write him down as a -1 power, do you know the number of people who do that mistake is really quite common? You think that is that. And I know why you're doing it. Don't you think the 4 and the x are like stuck together? So if the x becomes -1, the 4's still going to be beside it. But isn't that guy actually this one? So that's right and that's wrong. Do you see the difference?
Would it
So-
be correct if you put parentheses around the 4x?
You would, but then trust me, that's not going to make your differentiation any easier, is it?
Yeah, and it would be awful.
It would be awful. So let's just bite the bullet and not do it, right? Let's just call it what it is and we're done. Right? So I'm just trying to explain why this little don't necessarily use the way it's written, but change it into something that makes life easier. Now, when they are difficult, like these ones are, you do the whole thing, right? The 1 plus derivative squared thing. So multiply by the power divided by new power, that's x squared. Multiply by the power, and then reduce the power by 1, you get that guy. Now I'm going to do 1 plus the derivative squared. So it's 1 plus all of this guy squared. Does that look like it's going to be a perfect square? Actually, eventually it is going to be. Right? It doesn't look too promising right now, but it is. I'm going to take this really slowly. I could have just wrote down what the answer is, but there's a lot of weird powers going on. Let's foil it. X squared times x squared is x to the 4. Agreed? X squared, I might do that on a new piece of paper. X squared times -1/4 x to the -2. What does that get you when you multiply an x squared by -1/4 x to the -2? What does that get you?
Don't you add the powers together so you get x of 0 or 1?
There's a long-winded way, but you're nailed it. Would you agree that that actually gets you the number -1/4? You comfortable where that's coming from? So that guy is -1/4. Now, if you do -1/4 x to the -2 times x squared, can you trust me? You just end up very similar answer, -1/4. So that's the I. Right, last guy. And I'll do that, I think, at the side as well. We want to do -1/4 x to the -2 times -1/4 x to -2. Okay, what will that eventually get you when you're finished? Okay, break into stages. What will the -1/4 times another -1/4 get me?
1/16.
Right, positive 1/16, correct. What will x to the -2 times another x to the -2 get me?
X to the -4th power.
That's the answer. You agree? I mean, there is a logic to it, right? It's not random. And so we have now got plus 1/16 x to -4. And I'm going to put x to the 4 first. I've got a 1, a -1/4, a -1/4, which is -1/2. 1 take away 1/2 gets me +1/2. And at the end, I have got 1/16 x to -4. Have you noticed that I've written them down in highest, middle, lowest? In other words, I've put them in order. Would you agree this is an ugly expression with at least 2 x's in it? And didn't I say that when you see an ugly expression with at least 2 x's in it, isn't there a very good chance it's a perfect square? And this one is a perfect square. That x to the 4 is going to give me this piece, and that guy at the end is going to give me the other piece. And just like we did last time, don't we use the square roots to figure out what goes where? So the square root of x to the 4 is x squared, and there's a plus there, so I'll put a plus. What is the square root of 1/16 x to the -4? What would the square root of that guy give us?
1/4 x to the negative 2.
And now you're going to trust me, but check it if you don't, that this guy, if you FOIL him out, you get this guy. And you might say, what about the half? The half sorts itself out. It's there, right? It works. But you don't need to worry about what that is because these two guys take care of it. So we now have the arc length is the integral. Oh, I forgot to tell you where this question starts and finishes. So let me tell you, it starts at 1 and it finishes at 2. So it's going to be the integral from 1 to 2, the square root of this guy. But square roots and squares work really well together. And so our integral just becomes that guy. And I can do a power rule on him. Add 1 to the power, divided by the new power. Power rule on him. And we're going to evaluate it at x equals 1 to x equals 2. This time I'm going to make sure that I do my style point thing. It's just much easier to deal numerically with this guy than it is with these guys. So plug in 2, what do you get? 2 cubes 8, so you get 8/3. Put 2 here, you get take away an 1/8. That was easy. Minus, plug in 1, you get 1/3. Plug in 1 here, you get 1/4. So our answer is 8/3, take away an 1/8, take away 1/3, add 1/4. And I don't want to do that. Let's the calculator do it for me. So here goes. 8/3, take away 1/8, take away 1/3, add 1/4. So when I hit enter, I get horrible decimal, and then I just go math, number 1, and the answer is 59/24. Isn't that much safer than me trying to do it by hand? We agree? 59/24. My impression of these questions so far is that the vast majority of what we do is algebra. Aren't we foiling things and factoring things, right? And making them into perfect squares. And a little bit of it at the beginning was one differentiation and a little bit at the end of integration. Isn't the big chunk of work in the middle all algebra, right? Having to deal with expressions, and in most cases, at least in these ones, make them perfect squares. I think that one went down okay, considering how ugly it was. You feel comfortable about the process? Right. Let's find another one. Oh, God, there's some good ones here. Last one for today. And this one looks like that, right? So would you look at that guy and say, chain rule? Agreed? Differentiate the natural log cosine x. You get 1 over cosine x times the derivative of cosine x, which means that we now have
Negative tangent.
Oh, well done. Yes, I didn't. You nailed it. That's exactly what I was going to ask. Can that guy be something else? Now, if you do 1 plus the derivative squared, won't you get 1 plus negative tan x squared? So, you know when you go into trig identities take over, right? So you got to have a different mindset with this question. And negative tan times itself is just plus tan squared. Do you know anybody who looks like 1 plus tan squared?
Secant squared.
Secant squared.
Agreed. So haven't we made this a perfect square, but for a totally different technique? So our arc length is going to be the integral from 0 to pi upon 4. The square root of this guy, dx, which becomes the integral from 0 to pi upon 4 secant x dx. And this guy, technically speaking, belongs to the I have got a good memory, but I don't think we've ever done him. So let me tell you who he is. So will you just, you might want to check this because it's so long since I've done a secant on this one, but I believe this is it, right? And so the integral of a secant is this guy, and you evaluate it at 0 and at pi over 4. So you just trust me, it's one of those guys you're just meant to know. Actually, you're meant to look it up at the back of the book. If you get really stuck in the e-book on an integral, right somewhere at the back, I can't quite remember, there's like 300 what are called standard integrals. One of them is this guy. So you just find it and write down what the answer is. Yeah. With a few exceptions in the human race, would you agree you probably can't memorize 300 standard integrals, right? 300 guys that you just meant to know that's the answer, right? I think we have, what, about 10? Would you agree if I said secant squared, you'd say, oh yeah, I know what that one is, right? If I said sine, you would know what that one is. But there we go. So anyway, it's going to be the natural of secant pi upon 4 plus tangent pi upon 4. Take away the natural log of secant of 0, tan of 0. Okay. The secant of pi upon 4 is the same thing as 1 over the cosine of pi upon 4, which is 1 over root 2 over 2, so it's 2 over root 2. This guy is 1. Take away secant of 0 is 1, tangent of 0 is nothing. And so what am I looking at? I'm looking at the natural log of 1 plus well, if it's made that look pretty, it ends up being root 2, doesn't it? Yeah, it does. And that's nothing. So there's your answer. The natural log of 1 plus the square root of 2. And well, I did a couple of, you know, in my head things, but hopefully you can figure them out if you look at them. Right, last name and bye-bye. And we learned some cool stuff today.